Hello, this is Greg Risteman from Olympus. I'd like to welcome everyone today to this webinar titled Acoustic Influence Map, AIM, the modeling tool for your TFM inspection. In this webinar, you'll learn the importance of modeling when using the total focusing method, TFM, and its different wave sets. The webinar will cover the usage of the AIM tool with features like the sensitivity index. Lastly, you'll learn how AIM can be helpful in probe selection for a given application. Our presenter today is Emily Peliquin. Emily is a Global Advanced Product Support Manager here at Olympus and has been working in the welding NDT industry since 2009. She holds an associate degree in applied science and is trained in accordance to SNT TC 1A for level 2 on all major NDT methods. Emily joined Olympus in 2013 and has held positions ranging from technical support to product management, focusing on ultrasonic, phased array, TFM, and other advanced inspection technologies. This informational webinar has been scheduled for approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the live webinar, they will be addressed either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Emily. Emily, take it away.
Thank you very much, Greg, as usual. Thank you for the introduction. And thank you, everyone, for joining. We're glad to see that this subject seems to generate a lot of interest. And so thank you for being there. Thank you for attending. So as Greg mentioned, today we're going to talk about AIM, or Acoustic Influence Map, which is a modeling tool directly on board of the OmniScan X3. So the agenda for today, first we'll do a quick recap of what is TFM, or Total Focusing Method, and what are wave sets. Then we'll look at which wave set we can use for different scenarios and which probes to use. Then we'll look at the AIM basic principle and how it works. After this, we'll look at the tool named sensitivity index within the AIM modeling. And after that, of course, we'll look at some results and the conclusion. So first off, what is TFM? So since we are on our third webinar on the TFM series, I'm not going to spend too much time explaining the basic principles of TFM, but you're welcome to go online on Olympus-IMS and to view our former webinars on the subject if you want more details. But we'll start with a short description of what TFM is. So TFM stands for Total Focusing Method and is an image that is based on the elementary A-scans data that we collected through the full matrix capture, or FMC, acquisition. The TFM image is generated by applying sum and delay processing to all the elementary A-scans using expected time of flight of the selected wave set to a specific point or specific pixel. This is done for every point in a grid that is selected by the user that we call the TFM zone. And because every point in the image is reconstructed with the optimal focus, the resulting image is said to be focused everywhere. So now, what is a wave set? So a wave set is what we would call, there's two different groups. So pulse echo type of wave sets are the following that we see here. So LL, TT, or 4T, L standing for longitudinal, T standing for transverse, would be wave sets that we're fairly used to see because it is similar to what we have used in the past with phased array, where the sound is coming out of the probe and then going to the reflector and then back in the probe. So that's what we call pulse echo. But with TFM, there's also new types of wave sets that have emerged and that are fairly new for phased array users. So we call them self-tandem modes, also known as indirect paths or imaging paths. And those would be your TTT, TLT, and all those that you see here. So those modes are actually modes that will bounce off come out of the probe, bounce off the back wall, as we can see here, and then going to the reflector to then go back into the probe. They can have also more complex, like we can see with the 5T here, but usually there is an extra bounce before coming back into the probe. So these wave sets have shown to be able to image defects that we couldn't easily detect with phased array in the past. For example, an ID crack or sidewall like a fusion, things that are very vertical might have different wave sets to be able to image them better, which we'll look at some example in a little bit. So how do we select the right wave set? How do we know which one will work the best for a given inspection? So there is, as I mentioned, many advantages and limitations to some wave sets. And so in the limitations, it's important to understand that if we don't select the proper wave set for a given inspection, we can miss defects altogether. So to prove this, or just to show as an example, what we've done here is that we have a phased array probe on a resolution block, and the probe is looking at these sidral holes here, the arc of sidral holes in the resolution block. So what we're showing is that without moving the probe at all, we only changing the wave sets, and we have obviously different results with different wave sets. So in TT, what we considered pulse echo again, it would be very similar than what we would look at with phased array, where the sound is going to the defect coming back into the probe. And here, as we can see the sidral holes very well with a nice resolution. Using an LL wave set, well, with this configuration and the type of wedge that I have here, it's not the optimal for longitudinal, but as you can see, I can still have some detection. Now, as soon as I move to an indirect path or a self-tandem path like TLT, the sound is expecting to go back to the back wall and then to the reflector to then go back into the probe. But this setup is not optimal for this kind of wave set. So I'm losing entirely those sidral holes from the screen. They disappear. And same thing here in TTT. So it is very important to know what we're going to look at before selecting the wave set to know which wave set is the proper one for the inspection. So here are some other examples other than sidral holes. So we're looking at here a sidewall lack of fusion, and we're looking at the sidewall lack of fusion from the same side. So the probe is on the same side as the defect. So here, using TT, again, pulse echo, very similar to what we would see with phased array, because we are on the same side and we're sending sound directly and then it comes back directly, the angle of incidence is really not optimal here. And so I'm not seeing anything on my screen. With longitudinal, very similar here again, and again, not the optimal setup for longitudinal wave. And so again, my screen is not showing anything, even if it is a large reflector. Now in 3T, what we're doing is that we're sending the sound. So this is an indirect or a self-tandem wave set. And so we're sending the sound to the back wall. It's coming to the reflector and then going back in the probe. But again, because we are on the same side, the reflectivity or the perpendicularity is not optimal. And so I'm really not detecting anything here again, even if it is a self-tandem mode. But now with the 4T, I really have a nice reflector. So now I'm seeing it. I have a very nice resolution as well. And so what happens here is that we're sending the sound to the back wall. It's bouncing on the defect, coming back to the back wall, and then back in the probe. So now we have a very optimal angle of incidence, and therefore a very large reflector, and we can image it very well using 4T in TFM. Now another type of defect that would be a root crack, And so looking at here, the LL waveset, I can see that there's a little bit of something going on, but again, with this setup, LL is not optimal. Now going to TT, which again is very similar to what we used to see with phased array, transverse, with pulse echo mode. So I have a similar result that what I would have with phased array as well, which is a strong corner trap and a little bit of tip diffraction. So a knowledgeable phased array inspector would know that this is actually one defect. It's one crack that is being one single crack here. And so they would know that the crack would stop at the tip diffraction. But for somebody that is not used to phased array, this might not be that obvious that the defect can be quite large. Using a 4T here, for example, we see again a little bit of the corner trap, but the tip diffraction is a little bit less obvious in this case. So trying with now a 3T, now we can image the vertical crack very well. And so we can see also, we don't need experience to be an experienced user to see that this is one single defect and that the crack is vertical here. And so that's the advantage here. We can image with the 3T for this specific root crack. We can image the defect very well. So how do I know? How do I know which wave set should I use for my inspection? Should I try all the 10 different ones? Is that going to be effective? And so unfortunately, there's several factors that can impact the wave set selection. And this is why modeling is so important for TFM. So a probe in hand or experimental prove-up is unfortunately not accurate. It's not a good way to prove or to confirm which wave set we should use in TFM. So even if I was to change all my 10 different modes and try them all one by one, unfortunately, there's other factors that affect the wave set selection, like the type of flaw that we are looking for, the depth of that flaw, even if it's the same type, the flaw orientations or the angle at which that flaw is, and also the probe characteristics and other things that we're going to look at. Now, how to select the right probe for the TFM inspection. So TFM, as we said, is expected to be focused everywhere. But depending on the probe that we're using, we will have different results. So even if I'm selecting here with my zone, I create a zone around all those holes like I did here, even if I am in TFM and I am focused everywhere, the physics of ultrasounds cannot be changed. And so that's what we're showing here, that depending on the pitch and the frequency and the general characteristic of the probe, the results may vary. And so we'll look at this in a little bit. But let's look now at the basic principle of the tool AIM. So what is AIM? So again, AIM stands for Acoustic Influence Map and is on board of the OmniScan X3 flaw detector. The goal of the tool is that it enables the inspector to create a scan plan that maximizes the signal-to-noise ratio of the TFM image and increases the probability of detection for a given flaw. It displays the expected ultrasonic response for a given waveset and a given reflector. So it assists the user in selecting the optimal waveset, and it gives also, as we mentioned earlier, a sensitivity index, which we'll look at in a little bit. It is an essential tool for TFM because, again, we cannot simply go and try them all one by one, all the wavesets, because there's just too many factors that influences the waveset selection. So we need to create a scan plan in TFM. We need modeling. So here's what the user will have to select. So first, we can see that there is two different types of flaw. And there is a spherical, which would be for indication like, for example, porosity. And planar for example, like we looked at earlier, so the crack, OD crack, ID crack, sidewall lack of fusion, and so on. If the user selects planar, then they'll have a box to enter the orientation of that flaw or the angle of the flaw. So negative, as we show here, would be tilted towards the probe, when positive on the other side will be tilted away from the probe. So again, in the example that we had earlier, here for a 40, I entered 32 negative because the lack of sidewall fusion was tilted towards the probe. It was on the same side as my probe. And so the AIM model is for this configuration of a 32 angled flaw, planar flaw at 40, was showing me here that I had a very good coverage and a lot of energy for at any depth in my part. So a bit less as we go at the very top of the part and a bit less at the very bottom of the part, but still I can see that I have a good coverage with a good sensitivity. So this is how I selected that this was the right wave set for my inspection. Now let's see how the AIM modeling tool looks like on board of the OmniScan. So this is the scan plan on board of the OmniScan. So after selecting my part and weld, my probe and my wedge, like we see here, I'm now in the third tab of the scan plan, which is groups. And so from groups, I will select the law configuration, and I'll change from sectorial to TFM. So as soon as I do that, I am now in a TFM inspection method. And so I can see the pulse echo type of wave set in LL, and it already generates a map, an AIM map for this. So directly as soon as I enter the TFM, the AIM will be automatically displayed. As I change from one wave set to another, like here I'm in TT, you can see that the AIM modeling is also adjusting. And now if I go to self-tandem, again, the model is adjusting for all of them. So now in TLT, TLL, and so on. So you can see it moving and adjusting. And now if I go to planar, this is where, again, like we change the type of flaw. And so I can see that for example, here in 5T, if I was at 0 degrees, so 0 degree would be for something vertical, like the ID crack that I had earlier. So here in 5T, it shows me that if I still had my ID crack at the bottom, I might not be able to detect it with the 5T. Most of the energy is at the top of my part. So as I change the angle, the map is adjusting at the same time, as you can see here. So now if I entered for a lack of sidewall fusion, like we had earlier, so negative 32, and towards the probe means that my lack of fusion would fall here. So for this 5T, it shows that at the upper part, upper section of my part, I have a little bit of energy, but not much, and but next to nothing at the bottom. So that wouldn't be the optimal setup or wave set to select. So now I'll change for self-tandem, or I'm sorry, pulse echo, but 40 here. And now, as I showed earlier, I can see that I have a very nice coverage and that my energy would be enough at the bottom and at the top as well to be detecting with a higher sensitivity. So this was how to select the right wave set, but now how to select the right probe using the AIM modeling. So again, the same 3 probes that we had earlier, It's just like with phased array, it is not possible to focus past the near field. Even if we do say that we are focused everywhere, if the probe is not capable of that focusing capability, then it's impossible to have a zone that will be focused everywhere. So we need to be very aware of the limitation of the probes. So here's how AIM can help here. And so for the A2 probe, the first probe that we have is a 2.25 megahertz with 64 elements and a 0.75 millimeter pitch. Here, my probe is sitting on my part. I am in direct contact here though, so that's why you're not seeing a wedge. I don't have a wedge. I'm directly in contact like we represented here. And so we can see that the AIM is showing the energy at the top of the part. And this is also what my scan was showing. Once we were in acquisition, that's what we were seeing, that the AIM was right. We don't have much sound at the bottom of the part for this probe configuration. Now for A2 again, but with this time a 5 megahertz and a different pitch as well, 0.6 millimeter pitch. So my sensitivity has dropped just a little bit, but I can see that I now have more energy at the midsection here of the part. This is also what the scan confirmed. So I'm now able to have a resolution and to see these holes. But again, same as earlier, I don't have any energy at the bottom of the part, and this is also what we represent here, very poor resolution here. Now with a Pipe Wizard 1 probe, so that's a 7.5 megahertz, 60 elements with 1 millimeter pitch, we can see that the AIM is showing a much better coverage at the bottom of the part. So we have a lot of energy here, a little less at the top for near surface resolution. And this is exactly also what the scan is confirming. So we have a good energy everywhere, but a little less as we saw at the top of the component. So depending what you're inspecting, this is how you can select the right probe. So if I don't need much resolution at the bottom of the part, this can confirm if I'm going to have a good coverage or detection or no detection at all. So it's a very good tool, even if you don't own the probe physically, if it's not in your inventory. As long as it is on the probe library directly on board of the OmniScan, and then you'll be able to use the AIM tool for it. So you can build a procedure even without having the probe yet in your inventory. And now the sensitivity index. So we mentioned it a little bit earlier. So what is the sensitivity index? So AIM predicts the acoustic beam coverage for each combination of wave propagation path or wave sets, so the inspector can optimize the TFM scan plan to increase the probability of detection. So since the AIM map is self-normalized and displayed in a constant amplitude scale from 0 to minus 15 dB, the color maps requires a value to represent the relative acoustic sensitivity between the different TFM scan plans. So basically what we mean here is that the color red that we see everywhere, or the blue or the yellow, is the same color everywhere. However, it's not always the same value everywhere or the same energy everywhere. And so we use the sensitivity index to normalize and to understand what that red means from one scan to another. So the sensitivity index reading is displayed on top of all AIM maps to facilitate the comparison of each wave set's efficacy. The sensitivity index is simply the maximum amplitude of each AIM map prior to that normalization. The sensitivity index is displayed in arbitrary units that are proportional to the predicted voltage amplitude at reception. By combining the information of the AIM maps along with their sensitivity indices, you can obtain the better comparison of the acoustic sensitivities of different TFM inspection setups. So it really helps to be picking the optimal setup. So here's a few examples of the sensitivity index in action. And so here on this example, I have a 7.5 L32, so 32 elements, A32 probe with its wedge SA32 and 55S wedge. And now for this AIM map, I'm looking at a 3L in self-tandem. And I have a very poor sensitivity, as we see here. So again, LL was not optimal for this setup, so that's why we picked it as an example. But now that I switch for 4T, I increase my sensitivity index. And so another way that I like to look at the sensitivity index is it's like if we compare the AIM map to a heat map. And so basically there's no limit of how the temperature can increase. And so, but we do know though that in this case, the hotter is the better. So there's no hard limit of where the temperature can stop, but we are aiming for hotter temperatures. So here we replaced, instead of having the previous 7.5 megahertz, now we replaced it with a 10 megahertz. And so you can see that we have a slight increase also in sensitivity. So we went from 41.37 to a 46.52. So adjusting the probe, not just the wave sets, but the probes as well, can increase your sensitivity in your setup. So let's look at some results on actual indications. So here, the same sidewall lack of fusion that we were looking at earlier. Now, at a slightly different angle, we entered the 30 here instead of 32, but still using the 4T. We have a very nice resolution of as the AIM was predicting here. Now, for our OD crack, we can also see that with the 5T here, with the planar mode selected at 0 degree, because we know that it's vertical. So it was predicting to see it very well here at the upper part of the component. And so as the scan here is showing us. But here as an example, if I change for 2T, I still have some energy here. I can still see that there's colors at the top of my part, but my sensitivity index has dropped considerably. And so that's also what our scan is showing us, is that the signal to noise ratio is not as good for this specific scan. So that's how also we can use the AIM in knowing and predicting what kind of detection in signal to noise ratio we're going to obtain. Now for some different defects with ERW as an example. So ERW is electric resistance welding. It has been in the past a challenging inspection for ultrasonic just because of the multitude of different ways that the defects originate from those welds. And often the reflex can be very vertical, which can be difficult as a reflector to image. And so TFM was definitely a good prospect for these kinds of defects. So what we've done here using the AIM, we selected the optimal wave sets that could image the different defects that we had in our component here. And so what the AIM was proposing was using TT, 4T, and 3T. We could have used up to 4 modes at the same time using the same probe for the same acquisition. So we could have add an extra up to 4 groups. But since the AIM really seemed to cover all the types of defects with those 3 groups, we simply went with 3 here. And so the first flaw that we were trying to image is the stack lack of fusion here. And so those can be challenging, again, just because how vertical they are. But as you can see here, the 3T was the one who picked it the best here. So the green dot represents the active mode here on the right. And so we can really see the two different stacks lack of fusion and the space in between them as well. So this was 3T was the mode that was representing or imaging the best for this kind of defect and this curvature as well. Because you know, keep in mind also that the more we have bounds to the back wall, the more the geometry will affect which waveset we need to select. And so 3T for this geometry might not be, and this type of defect might not be the same as on flat. So I might not image it the same way. So that's why it's important to use the modeling tool for every kind of geometry that we are using for every inspection. The second flaw is ID over trim. Again, we had detection on multiple wavesets here, but the one that imaged it the best was the first one here, TT, but we can see that we picked it up on the other modes as well. The third flaw here is an OD hook crack. Hook cracks can also be challenging to detect. And so here, the mode that we see it a little bit in 3T, but the mode that detected it the best was in TT. And so this is the resulting image. And lastly, the flaw number 4 that we had is a ID hook with a branch crack. And so we were detecting it very well with the 4T here, with a very vertical reflector, but also we were able to catch the tip diffraction of that branch crack here on the side. So that's why we decided to go with the 4T. So finally, so why is modeling so important when we are doing a TFM inspection? So again, the proper waveset are critical, as you saw, for the detection. So if I don't have the right waveset, some indication can disappear from the screen, even if they are large reflectors. There are many wavesets to select from, about 10 waveset or more, and so it can be very confusing for the inspector to know which one to use. The orientation of the flaws will impact which waveset you need to select. And so there's really no way, again, to have a probe in hand to try to confirm with side drill holes or even with some cracks. You know, if it changes a little bit, you'll need a different waveset. And so probe in hand with a block is just not the best way to select, to do a waveset selection. Then, as I just mentioned as well, part curvature or part geometry can also impact the result. And so without being able to model that, it's impossible to select the proper waveset. Then focus is also in TFM expected to be everywhere in the zone that the user created. And so we really need to confirm that the proper probe, the proper pitch, the frequency, all of this, how it affects our signal, and if it is proper for the inspection that we're trying to do. So in summary, AIM is a modeling tool on board of the OmniScan X3 flaw detector that helps the inspector predict which waveset will obtain the best result. It also helps the inspector predict which probe will obtain the best results for the given inspection. And again, because there are just too many variables, modeling is necessary for TFM inspection, and a probe in hand prove up is simply not effective. That's all I had. Thank you very much for your attention.
On behalf of Olympus, I'd like to thank all the attendees for joining us today and Emily for her expertise and participation in today's event. We hope the material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thank you again for your interest and taking the time to attend this event. We'll see you again for the next Olympus webinar.